So hello, thanks for being here. Today we're going to be talking about a series of offensive wireless techniques that can be applied to physical and MAC layer technologies. And the reason why we're really excited about this content is because the growth of mobile and Internet of Things focused technologies means that wireless technology is more diverse and incumbent across all industries and domains than it's ever been at any point really in modern history. And with this massive expansion of wireless technology comes basically the introduction of many new attack surfaces that we as researchers can research and exploit. So I'm Matt Knight. This is Marc Newlin. We're both security researchers with Bastille. We're really excited to be here. We spend almost all of our time thinking about wireless topics, and we're excited to be here and share some of our findings with you today. So we're going to begin with some background, both a little bit of kind of industry context and history, as well as some technical background. And this is just enough to frame the conversation and provide enough common vocabulary so that we can talk through what we're calling our methods of wireless exploitation. And that's the real body of this talk. So what we've done is we've looked at a series of high-profile wireless attacks that have happened in the last couple of years. And we've broken them down into categories based on kind of their distinguishing features. And for each one, we're going to talk about the mechanics of the attack. That's the technique, the impact, and mitigations against them. But then, most importantly, we're going to highlight analogs to similar attacks on wired networks where they exist. So the purpose there is to provide as much of a basis towards understanding wireless networks and kind of the security issues surrounding them, so that even if you don't have any wireless expertise, you'll still be able to translate your network security expertise over and be able to think about these networks kind of creatively. And finally, we're going to wrap it up with some examples and demos to kind of bring it all home. So to begin, I'm going to provide a little background on kind of the development of wireless network security technology. So if you were an IT admin or a security professional in the 1990s and you wanted to begin to inspect your networks at a low level, you really had two protocols to be concerned with. You had 802.3, which is Ethernet, and 802.5, which is token ring. And if you wanted to be able to inspect these protocols at a low level, it likely involved running proprietary packet sniffing software on an expensive proprietary computer like this. Not very flexible, expensive, not that great, not that friendly. Fast forward to 1998, and something interesting happened. Ethereal was released, and Ethereal has since rebranded to become Wireshark. It's an open source packet sniffing technology that made great steps to making this sort of network layer inspection really commodity and much more accessible. So we like that. So fast forward to the 2000s, and the list of protocols that you're concerned with is a little more complicated, right? So 802.3 and 802.5 are still in there, but in addition, you have all these other technologies. And if we were to break this out and really take time reading through it, you would see that most of these are wireless. So if you wanted to look at these wireless stacks in the early 2000s, it likely involved getting your hands on an early software-defined radio. These could easily cost six figures, very expensive. You needed a large, computing backend, behind it to support it. Really restricted this technology to primarily academic and government groups. So, not that accessible, not that friendly. Fast forward to 2012, and something really interesting happened. A Finnish hacker named Antti Palosaari, I believe his name was looking at his DVB-T USB stick. And DVB-T is the digital video broadcast system that's used in pretty much everywhere in the world except North America. So if you want to watch television, you don't want to pay for cable, you can get rabbit ears and plug them into your TV and get HD video over the air on DVB-T. This is a commercial DVB-T USB dongle. This researcher was looking at it, discovered that there was a debug mode in the RF front-end chip that if you set a register a certain way, you could bypass the demodulator and stream raw IQ information back to your host over USB. So with a promiscuous driver, you turn this thing into a poor man's software-defined radio. And at $8, we like that. So fast forward to 2017, and SDRs are a dime a dozen. You have tons of different technologies that satisfy virtually every capability at every different price point. So SDR is fully commodity. Pretty much the entire wireless domain is in scope now for security researchers. So wireless in 2017 when we talk about kind of the evolution of the space, it's important to remember that 802.11 Wi-Fi is really just one piece of the puzzle. And that the growth of IoT and mobile technologies means that there's a physical layer for every use case. And increasingly, these physical layers are being used to connect embedded systems. And we understand embedded systems to be really designed around compromise. Oftentimes, they run on battery, so they're limited with the type of computation you can do on them. They may have limited user interaction, so limited kind of configurability once they are deployed and applied to the field. For good or not so good reasons, they may either have limited or no encryption. Additionally, they may have limited network access to them, such that deploying firmware to these devices might be either difficult or impossible. Additionally, many of these devices, to save costs, will use one-time programmable memory, so they can't even be delivered firmware at all. And to kind of illustrate how complicated this can be, I want to draw your attention to the picture on the left there, where in frame but invisible to the viewer are three literal embedded systems. They're traffic sensors that are buried in concrete. So as you can imagine, getting firmware to those things is a lot more complicated than Patch Tuesday. You can't just send a patch to that thing because it's a proprietary wireless technology that's connecting to it. And if something happens to that link, you're sending a team of guys with concrete saws out there to dig these things up and replace them. So very complicated. When you combine that with the fact that there's a historical industry reliance on security through obscurity, that means for us as researchers, we have loads of targets that are highly vulnerable. So with that, I'm going to hand it off to Marc, and he's going to keep things moving.
So as a security practitioner, you're probably familiar with using tools like Wireshark to look at layer 2 and higher network traffic. And we're looking at layer 2 and higher traffic because you're getting these packets from something like a Ethernet card or perhaps a Wi-Fi card or Bluetooth radio. And the data you get from that hardware is layer 2. So because of this, you can't use these devices for looking at layer 1 traffic. And if we look on the left here, we have a picture of a spectrogram. And from left to right, we have a few different wireless physical layers. And you can see just visually they're very different, and that's because the physical properties of these physical layers are different. And so that means we can't use something like our Wi-Fi card to look at these different protocols, and we need more generic type of hardware. And so to do this, we use something called a software-defined radio. And unlike a Wi-Fi card or a Bluetooth card where the logic that speaks that specific protocol is baked into silicon, an SDR is a more generic, reconfigurable radio front end. So we can tune it to different center frequencies and set it to different channel bandwidths. And then the SDR sends this raw radio IQ data to either an FPGA or to a host computer. And then we have software which defines the physical layer of how each different protocol operates. And this has some good benefits. So one, we can use one piece of radio hardware for multiple different protocols. And then we can also iterate very quickly on our software. So if we're reverse engineering a wireless protocol, we can iterate on our software as we figure out more about it and don't actually have to change our hardware. So it's a pretty useful tool. One of the problems with software-defined radio, or at least perceived problems, is the complexity and the esoteric nature of the field. And on the left here, we have some RTL from a 802.15.4 decoder Matt implemented for an FPGA, and it's nice and clear what's going on there. But a lot of people think SDR is this complicated field, but it really doesn't have to be. And Matt and I have spent a lot of time trying to figure out how to make these SDR and RF physical layers easy to understand. And to that end, we've given a series of talks called So You Want to Hack Radios, where we discuss our strategies for reverse engineering wireless protocols. And if you want to learn more about that, the video from our Hack in the Box Amsterdam talk is up on YouTube. One of the tools we really like to use with software-defined radio is called GNU Radio. And this is an open source digital signal processing suite, and it abstracts away all of the complicated math and signal processing that you need to use for SDR, but you don't need to actually understand. So both Michael Ostman and Balint Sieber have some good videos up on YouTube about SDR in general and GNU Radio. On the right here, we have a picture of GNU Radio Companion, which is a drag-and-drop flow graph creation tool with GNU Radio. And this allows you to visually drag and drop different DSP and signal processing blocks and implement your transceivers, receivers, and transmitters visually without actually needing to understand how the underlying math works. And so I never went to college, for example, and I'm able to use GNU Radio to do really interesting work in this space. So it's a very valuable tool. And now Matt is going to walk you through some of these basic RF concepts that we'll need to understand the rest of the talk.
All right, so the purpose of this next section is basically just to provide the vocabulary for all of us here so that we can kind of understand what makes wireless unique from wired networks as we begin to work through the various attacks later in this talk. So when we talk about wireless technologies, we're invariably involving the physical layer. The physical layer is essentially the lowest layer of the communication stack. And in wired protocols, it defines how our digital ones and zeros get mapped into electrical phenomena. And that's voltage, timing, and wiring information that comprises what's a 1 and what's a 0 in electricity. In the wireless medium, or in wireless technologies instead, we're defining how those 1s and 0s get mapped into patterns of energy that are being conveyed over the RF medium. And the RF stands for radio frequency. It's essentially the electromagnetic energy that's around us all the time. It's continuous, right? It's analog, but we can basically encode digital information into it. And the important thing to remember is that RF is comprised of an infinite number of frequencies. So we can represent channels as existing at different frequencies and at different bandwidths. So if we manipulate RF, we can begin to put together a physical layer. And manipulating RF is done with a radio. As Mark mentioned earlier, they can either be hardware-defined, as is the case with the LoRa radio on top there, or they can be software-defined, as is the case with the B210 below. But the core function when we begin to talk about physical layers that we need to really understand is called the modulation. And the modulation is a function that defines how your digital 1s and 0s get mapped into that energy. It basically defines what that mapping is in your specific PHY. So if you've ever written networking software, you've probably worked with an API where at some point you call API.send and you pass in a buffer, and then something happens to make your information appear somewhere else, either another system on your network, or maybe you're sending it to a radio and the radio sends it out over the air. But what actually happens once you make that call? So we're going to talk briefly, just with the next few slides, about what happens within the radio chipset to turn your buffer into energy that goes out over the air. So you have your layer 2 frame. You call an API and pass in the buffer, and then this goes out over some interface to your radio IC. It might be I2C, it might be PCIe, it could be SPI. It gets written out into your radio chip. The first thing your radio chip is going to do is it's going to prepend and append some information to create the PHY frame. So it's going to prepend a preamble and a start of frame delimiter, things to basically provide synchronization elements within the frame for a receiver to leverage. And then it's going to append a CRC. That's a checksum so that the receiver can validate that what it's received is coherent and valid. Then the modulation is going to be performed. Again, this is the function that maps your 1s and 0s into the electrical and RF and radio phenomena. So the modulation takes your physical layer frame and turns it into a waveform. It basically takes your digital 1s and 0s and turns it into this analog wave. That gets pushed out to your antenna or perhaps an RF front end, and it goes off into the air into the electromagnetic spectrum for it to be picked up by a receiver. So receiving is quite a bit more involved. So essentially, the receiver captures the waveform on an antenna, and it performs the demodulation, which is the inverse of the modulation function. But then it gets run into the physical layer demodulating state machine. And if you were to parse this out, it looks kind of like this. It's very complicated. We're not going to cover this in detail. If you want to understand how physical layer state machines work, that's what our So You Want to Hack Radios talk at Hack in the Box Amsterdam is all about. The entire talk is about how to reverse engineer wireless state machines. So check that out if you want to understand how this works. But essentially, we receive the analog waveform, we demodulate it, and then we run through the state machine until a number of conditions are satisfied, and the radios determine that it's received a packet. And then that packet gets presented through an API up to your layer 2 state machine, and you're off and running. The key things to take away from this is that radios are state machines, and therefore they're deterministic. So what happens here isn't magic. It's executing an algorithm that is going to do the same thing given the same inputs every time, and we can characterize that algorithm and find various clever ways to exploit it. Now, because the RF environment is complicated, by virtue of there being lots of contention from other emitters, we can begin to understand and factor that into our understanding of how these radio state machines are designed and how they perform under stress. So between all this, we have a number of opportunities to kind of creatively exploit and abuse these radios. So that brings us to the body of this talk, really what this talk is all about. And this is our methods of wireless exploitation. So what we're going to do is we're going to walk through a series of categories of wireless attacks. And these are informed by some of the high-profile attacks that we've seen in the last couple of years. So we've looked at them, we've broken them down based on kind of their defining characteristics and what they enable. And we're going to walk through them briefly with you now. So for each attack, we're going to discuss the methodology of how it's performed, the impact of what the attack enables, and number 3 is what we're most excited about. Wherever we can, we're going to provide analogs of these of similar attacks to these wireless attacks, but on wired networks. So if you don't have RF domain knowledge, you'll be able to leverage your wired domain knowledge to understand kind of the implications of each of these attacks. We're going to highlight some limitations and mitigations that you can use to defend against these attacks. And then we're going to provide examples in terms of recent real-world attacks and then demos as well. So to get started, we're going to discuss sniffing, and I'm going to hand it off to Marc.
So when you think about sniffing, you're probably thinking about something like Wireshark Layer 2 sniffing. But in this case, we're talking about sniffing the radio physical layer. And this is distinct from any type of wired exploitation. If you're going to sniff a wired network, you have to physically plug into it. But due to the inherently promiscuous nature of wireless, we don't have to be physically connected to anything in order to intercept somebody else's data. And we do need to be physically proximate to the network or device we're trying to sniff, but this is only limited by the amount of money we're willing to spend on amplifiers and antennas. So the big drawback to sniffing, again, is this range. So we need to be somewhere nearby it, but we can be hundreds of meters away in certain cases. A couple recent examples. Matt has demonstrated that you can sniff the pairing sequence that goes between the Zigbee door lock and the smart home hub. And by sniffing the pairing sequence, you can recover the cryptography keys and then decrypt the future traffic going on between the lock and the hub or intercept your own traffic. Last year, I did a lot of work researching wireless mice and keyboards, and I discovered that a lot of wireless keyboards on the market were actually unencrypted and therefore vulnerable to keystroke sniffing. So for a video demo here, we're going to look at the HP Classic Wireless Desktop Keyboard. And this uses an RF transceiver from a vendor called Mozart Semiconductor. And this was a case of security through obscurity. This was a proprietary, undocumented wireless protocol, but it happened to be a pretty simple GFSK protocol in the 2.4 ISM band. And after I had reverse engineered the physical layer, I discovered that it was just sending unencrypted keystroke packets over the air and therefore was vulnerable to sniffing. And because it's a simple 2.4 gigahertz GFSK protocol, which is fairly similar to the Nordic NRF 24L protocol, we're actually able to use this commodity off-the-shelf hardware with a little bit of Python code in order to sniff keystrokes from this keyboard. So for a video demo here, we're going to see on the left terminal bring up, we'll have the input from the keyboard, the focus from the keyboard. Then on the right, I'll be running a script which is going to decode these packets over the air using this off-the-shelf NRF 24L dongle. And then we'll see that we have the same keystrokes on both sides of the terminal. On one side, it's the focus from the keyboard. On the other side, it's what we're actually decoding over the air going between the keyboard and its USB dongle. And as we're typing on the left, we see the same characters on the right because, again, it's just this unencrypted protocol that's vulnerable to sniffing from a few hundred yards away. And now Matt is going to speak to you about Wardriving.
Cool. So Wardriving is really a variant of sniffing. Essentially, what Wardriving involves is sniffing wireless network traffic while scanning the output of it for identifying features of a protocol or device of interest. And optionally, you can make this technology active. That is, you can send out basically beacons or probe requests to attempt to induce responses from the infrastructure that you're looking for. So the impact here is it enables the attacker to enumerate and discover exploitable devices or networks within their physical environment. And if this sounds familiar, an easy analog to this is port scanning. Using Nmap to knock on doors on your network to see what's there, to see what services are available to exploit. So the limitations here are largely the same as what is the ones that apply to sniffing. However, the one thing we'll add to that is if you're scanning a number of channels and you only have one or a limited number of RF front ends, you'll have to timeshare them among all the channels that you're sniffing. So examples here, the classic Wardriving example is your 802.11 AP discovery Wardriving. And you think back to the early 2000s where you have people loading into cars with laptops and antennas and driving around looking for free Wi-Fi, plotting it on maps and then sharing them online, like kind of the classic Wardriving example of looking for free Wi-Fi. However, a more contemporary example that we'll discuss is actively beaconing for 802.15.4 network coordinator. So 802.15.4 is the physical and MAC layer standard that Zigbee is built on. And Zigbee is used for a number of home automation, industrial applications. It's a low power, kind of like locally focused wireless network. So we're going to show a video in just a moment. And essentially what I've done in the video is I've used KillerBee, which is a Zigbee network exploitation framework, to craft these broadcast beacon requests. And when those get sent out, if there's a network coordinator within the physical environment and it receives that request, it will respond identifying itself and providing some information about the network. And that's designed so that nodes that you're adding to the network can essentially identify the coordinator that they're trying to associate with. It's a feature of the protocol. But we as attackers can abuse that. So those packets are going to be sent out with the AppEmote hardware-defined radio board. And there's a picture of it there. It's essentially a good FET with a CC2420 802.15.4 PHY MAC chip bolted to it. So we'll jump over to our video here, and we'll see this in action. So on the left we have our transmitter, and on the right we have the receiver. And the transmitter is essentially hopping through all the 15.4 channels in the 2.4 gigahertz band. And you'll see when it hits channel 14, we get 2 responses back. So that means that there are 2 different coordinators present on channel 14. And if we let this run, you'll see it gets up to channel 26, which is the highest 15.4 channel in the 2.4 gigahertz band. We haven't received any traffic on other channels. We wrap back around and keep going. But we can assume that these 2 networks are present on channel 14. So we can then begin to look in more detail and identify other devices of interest on that channel. So the next attack that we're going to discuss is the replay attack. And the replay attack essentially involves retransmitting a previously captured physical layer frame. Now this can either be raw physical layer capture, like a raw IQ file that you've captured with your software-defined radio, or it can be a resynthesis of a previously captured packet. So if you've done the decoding and you have your layer 2 frame, your ones and zeros in a digital format, you can re-implement the modulation, feed that in, and regenerate it. They're both basically 2 different ways of implementing the replay attack. And this is an example of a command injection attack, where we can change the state of the network or a device or something on the network to essentially reproduce previously observed behavior. Wired or replay attacks exist on wired networks too, so there's no real interesting analog there other than you can do these there as well. So replay attacks can be mitigated against by implementing and then enforcing freshness and authentication. So freshness is a sequence number. So essentially what that involves is including a field within your protocol that essentially just tracks the index of each packet. So you just increase it by 1 every time you send a new packet. And then the receiver can track that so that if it sees a sequence number below the one that's expecting, or outside of some range, it can reject it because it's already received and managed that frame. Additionally, authentication can be combined with this to provide cryptographic authentication can be combined with this to provide even more security and guarantee of the message's authenticity. So an example we're going to discuss here is one from earlier this year. So at 1:30 a.m. on I think it was a Wednesday night in April, all 156 tornado emergency alert management sirens in the Dallas metropolitan area started going off. They look like that picture there. They're very loud. Essentially, because Dallas gets tornadoes, and tornadoes are really big events in the U.S. in the American South. They had this network set up as a means of alerting people to when they need to take shelter and take cover when there's going to be a weather event coming through. But so at 1:30 in the morning, all of these things started going off, and as you might imagine, that ruffled a lot of people's feathers. Additionally, when you consider that there had been some very public saber rattling between the United States and North Korea that week, there was actually some concern that this may have been an indication of some sort of a national security event. It was a pretty big deal. So we at Bastille have done some analysis of this event, and we've concluded that this attack was likely an RF replay attack. Indications given by the Dallas municipal group that manages these sirens, they basically confirmed that there is no encryption or auth on these devices. Additionally, they're tested quarterly, so every quarter, wireless transmission would be sent out to turn these devices on to make sure that the network is operating properly. It would be trivial for an attacker to use a software-defined radio to capture that signal and then replay it at a moment of their choosing, such as 1:30 a.m. on a Tuesday. If you want to read more about that attack, we have a blog post and some videos online that go into pretty good detail, so I'll direct you to that. Now I'm going to turn it back over to Mark, and he's going to take you through jamming.
So the closest analog to a jamming attack in the RF medium would be a denial of service attack against an IP network. And the big distinction is that when we're talking about jamming in the RF domain, we're talking about jamming the physical layer, whereas a denial of service attack is typically jamming layer 2 or higher on a network. And the purpose of jamming is that we can completely disrupt the flow of traffic on a network or disrupt the network state. And so a good example of this, you have Alice and Bob. They're trying to communicate on either side of a room. They're having a conversation. Donald comes in and blasts some nonsense that makes no sense, and he's so loud that he prevents them from communicating. And this is very similar to a jamming attack, except we're transmitting RF noise instead of audio noise. So the big problem with jamming, or one problem with jamming, is that a lot of modern devices will implement jamming detection mechanisms, which can alter their behavior if they detect an attacker trying to jam. The other problem is that if we're trying to sniff traffic on a network, and we jam at the same time, we can no longer sniff that traffic because we're jamming our ability to sniff the traffic as well. Our colleague Logan Lamb did some research into home security systems a couple of years ago and discovered a really interesting jamming attack. And what Logan discovered is that you can jam the wireless link between these door and window sensors and the control panel. So the normal behavior is that you have this sensor on your door or window, and when you open the door or window, it sends a wireless signal to the control panel to tell it that this state had changed, that it had opened or closed. What Logan discovered is that you can actually jam the RF channel used by this link and then open and close the sensor with impunity because it prevents the control panel from receiving that signal. And it does have a jam detection mechanism, but it was still possible to defeat. So for a demo here, we're going to show something we've recorded in a Faraday cage. And we've recorded this in a Faraday cage because it's generally illegal in most locations to do any type of an RF jamming attack. So here we have the control panel in the Faraday cage. We're currently jamming the link so we can open and close this door sensor without setting off the alarm. Now we're going to go over to GNU Radio. We're going to stop the SDR that we're using to jam it. And then as soon as we open it, it does trigger the alarm. So it's actually very trivial in this case to simply jam the channel and then walk into somebody's home and steal their home security system. And because we have different types of jam detection mechanisms, there are some smart ways that we can actually evade them. So when you have two wireless devices trying to communicate, it's in their best interest to not communicate at the same time because then they're going to jam each other. So a lot of protocols will use something called a clear channel assessment. And the wireless radio will listen on the channel it wants to communicate on. When it hears somebody else transmitting, it says, okay, the channel is occupied, somebody else is talking, I'm going to wait in line, then as soon as they're done, then I will speak. This actually gives them enough data to be able to detect a jamming attack. So for example, if we have a protocol that has a 9 millisecond packet length, the normal behavior would be for the channel to be occupied for 9 milliseconds and then go silent. If the channel is occupied for 10 milliseconds, this is longer than the average or normal packet length, then the device can say, okay, somebody's potentially trying to jam the channel and then change its behavior. So we can do what's called duty cycle jamming, where we'll in this case transmit for 9 milliseconds, turn off for 1 millisecond, transmit for 9 milliseconds, and go in the same pattern. And this way we can still effectively jam the channel without actually triggering these anti-jam jam detection mechanisms. And Matt has demonstrated this with some 8.0.15.4 jam detection and defeation using Killer B. It's another type of smart jamming called reflexive jamming, and this allows us to actually target specific packets or transmitters or receivers. So with duty cycle jamming or just plain basic jamming, we're just jamming the entire channel and not targeting any specific device. With reflexive jamming, we first try and receive any incoming packets, and we decode the header of that packet. And then we can make a decision to say, does this transmitter address or receiver address or some other criteria match what we want to jam? And then you can start transmitting as soon as you make that determination. And then you can effectively jam the second half or the end of the packet, cause a CRC corruption, and prevent it from being received. And this image here on the left is Sammy Kamkar's roll jam device, which is a reflexive jammer. And these are physical layer jamming techniques, but there's actually an interesting MAC layer jamming technique that we can use against 802.11 devices. So if I'm a Wi-Fi device and I'm transmitting a packet, I fill out the duration field in the MAC header, and the duration field defines how long I expect it to take to transmit the packet and receive an ACK. And this allows 802.11 devices to implement power savings. So if another device receives this duration field, instead of doing its clear channel assessment and keeping the radio turned on, it can simply turn the radio off for the duration specified by that field. We can actually take advantage of this by sending a 0-byte payload 802.11 packet with the duration field set to maximum. This allows us to transmit for a very short period of time, but trick other 802.11 devices into turning off for a longer period of time. And so with a single 0-byte payload link packet, we can effectively jam the channel for 32 milliseconds. And you can implement this with an ESP8266 or really any other wireless or Wi-Fi device that allows you to transmit raw packets. And this is a technique that was explained to me by Bastien Blocel at CCC last year, so props to him. And what we're going to do here for a demo, on one side we'll have a Wi-Fi client pinging a Wi-Fi access point. Then on the other side I'll have a one-line SCAPI script where I'm going to send 50 0-byte payload packets with the duration field set to maximum, and we'll see that we're able to effectively interrupt this 802.11 channel for several seconds just by sending 50 very short packets. So on the right, we have the client pinging the access point. On the left, with SCAPI, I just transmitted those 50 packets, and we can see that the ping response is stopped. Then in a few seconds here, it will pick back up, and we can see that by transmitting just 50 0-byte payload link packets, we're able to effectively jam the channel for several seconds. And this allows you to jam an 802.11 channel with a much lower duty cycle than traditional jamming and therefore save power. And now we'll talk about an evil twin attack. And this is analogous to an ARP cache poisoning or ARP spoofing attack on an IP network. It allows you to trick a victim device into connecting to your access point or base station. And once they connect to your access point or base station, you can then man in the middle of their traffic. And the big problem with evil twin attacks is that you need to have the same trust relationship as the device expects. So if there's authentication or cryptography, you may need to downgrade the cryptography or spoof the authentication. So it only works with certain types of wireless networks. The Wi-Fi Pineapple is a common out-of-the-box tool for creating an evil twin 802.11 access point. Then a lot of out-of-the-box IMSI catchers you can use, including the open source OpenBTS software. So for a demo here, we have a cell phone and a Faraday cage. We also have a software-defined radio in the Faraday cage loaded up with OpenBTS software. And OpenBTS allows you to mimic any GSM cell carrier that you'd like. And I want to point out that you should not do this. It is generally illegal anywhere to spin up a fake GSM base station, but it's also very, very easy. But don't do it. So here we have a cell phone in the Faraday cage, and we can see it's not connected to a network. Then we spin up the GSM base station by turning on our software-defined radio. Then in a few seconds here, we have the phone, it's connecting, and we'll get a welcome text message from our fake GSM base station. There we go, we have our welcome text message set up, and we can actually configure this to look like any cell carrier that we'd like. And now Matt is going to speak to you about malicious over-the-air firmware updates.
All right, so we're going to briefly cover this next topic. Essentially, a firmware attack involves first taking a firmware image, then modifying it to add some behavior to your liking. And essentially what we're able to do is we're able to exploit wireless over-the-air firmware update mechanisms if they exist within a device. So this would be, for example, being able to use 802.15.4 to send a new firmware image over a wireless link to one of those buried concrete or buried traffic sensors that we showed earlier in this presentation. So the impact here is it enables you to essentially add whatever behaviors you want to the device that you're targeting. And this can enable you to do things such as gain persistence on the device. You can do things like denial of service against it. One example from earlier this year was BrickerBot. There's a Mirai variant that essentially scanned the internet, found unconfigured IP cameras, pushed firmware to them, and then bricked them. And then additionally, you can self-propagate. So if you basically get a foothold on one device and it can talk to other devices, you can basically have your firmware then get updated from device to device and kind of keep going. And if this sounds familiar, it's because this attack is very similar to your traditional malware targeting endpoints. Things like worms in the self-propagating case. This is kind of like the wireless equivalent of that. So limitations here are that this kind of attack is defeated by essentially security best practices. If you implement any sort of code signing, such as secure boot, that makes it a lot harder to implement an attack like this. Additionally, having secure network encryption again raises the bar to make this type of attack more difficult. So two examples we're going to highlight briefly. One that I'll just mention is Cesar Cerruto's traffic light sensor Zigbee worm. He gave a talk at Black Hat, I think in 2013 or 2014, where he looked at traffic light sensors, smart traffic lights, determined that they were running on an unencrypted 802.15.4 network. He was able to sniff all the traffic, inject traffic, do things to mess with their state. Additionally, they used unsigned and unsigned firmware images on an unencrypted link to push firmware to the devices. So he went as far as to essentially postulate that it would be possible to make a worm using this. I don't know if he actually demonstrated it, but all the pieces were there. However, an attack that was demonstrated just about a year ago actually went that next step and demonstrated the worm in reality. And that's the worm that targeted the Philips Hue Zigbee lights. This was put together by a team of researchers. It was really impressive work. Essentially what they did was they were able to break the firmware signing key, or the firmware signing mechanism that Philips uses to encrypt their secure boot images. They did that with a really impressive hardware, I think it was a power analysis, like side channel attack. And then they were able to essentially deliver malicious firmware to these Philips Hue lights that not only would enable them to take them over and control their state, but would also self-propagate to other Philips Hue lights within range. So I'll direct you to their website. They have an awesome video where they deploy this attack to an office building, and they do it from a drone, because why not? And you'll see that they put a 15.4 radio on this drone, fly it up to the side of the office building, and then all the lights start blinking. It's pretty cool. And their paper's really good too. They go through this all in really good detail and show exactly what's possible with this type of firmware-based wireless attack. So this brings us to our last attack technique that we're going to discuss. And we're calling this physical layer selected targeting. But really this this captures a number of physical layer state machine-based exploits that we're going to detail here. So essentially, this involves fingerprinting various wireless chipsets and finding targeted ways to go after them. And I'll just kind of briefly introduce this. So when a new standard is released, the way that that's done is you have a bunch of stakeholders in the industry get together, and they discuss and determine what kind of features they want the standard to have, what they want it to look like. And then they take those ideas and they put them together into a nice, lean, easy to digest 4,000-page standards manual. Then that gets decided upon, it gets ratified, it gets pushed out. Industry players then go and pay a fortune to license it, and are then faced with the task of interpreting that standard. So they have to take that nice, bedside reading 4,000-page document, figure out kind of what the core technical elements are, and then convert that back into logic that then gets implemented in hardware. So these standards can be very long and very verbose, but they're not always completely defined. And even if they are well defined, oftentimes there are options, or there are opportunities for these manufacturers to kind of make decisions and inferences around the best way to implement things. So what that means for the chipsets is that not all chipsets are the same, and some of them have pretty distinctly different behavior. So essentially what we as attackers can do is we can fingerprint these chipsets and figure out how they perform differently. And then we can send standards non-compliant transmissions that are designed to exploit corner cases in some chipsets, but perhaps not all of them. So what this enables us to do is do some extremely targeted receiver evasion, which is useful in the case of doing a wireless IDS evasion, and also fingerprinting devices that are present within an environment. And this has been demonstrated on a wired network as well. This has been demonstrated specifically on 802.3. However, that's kind of a limited application because you're dealing with wires. The only scenario in which this kind of attack is useful is if you have a LAN tap type scenario. However, this is very practical in the RF domain, where because RF energy is promiscuous, you have it just radiating outward throughout free space, your physical environment. you have multiple devices within the same environment, multiple listeners, and this type of attack becomes far more impactful. So limitations here are that your network participants have to be on different chipsets. If they're all on the same chipset, they're all going to implement the same state machine. They'll all be have the same fundamental physical layer logic kind of running their performance. Additionally, not all chipsets are vulnerable to this type of attack, and even the ones that are vulnerable in different ways. So we're going to highlight this with by demonstrating 802.15.4 receiver evasion and selective targeting. So I have 3 radios that we're going to use in this demo. On the right, we have our transmitter, which is an app emote with the CC2420, and I'm essentially going to be changing the configuration of its physical layer to send messages that are compliant and then non-compliant in different ways, and I'll talk you through it in the demo. And then on the left, we have 2 receivers. We have an app emote with the CC2420, which we're keeping in its stock configuration. And then we have an RZ USB stick, which uses an Atmel 15.4 radio. So these are 2 different chipsets that are being used to receive. They have different physical layer state machines, and we're going to see how their characteristics and behavior differ. So what I'm going to do is I'm going to use my transmitter to send a series of 802.15.4 frames. I'm going to start by sending 5 protocol-compliant frames, 5 normal 15.4 frames. And then I'm going to start to mess with the PHY. I'm going to begin by adding 2 extra symbols to the preamble, and then I'm going to continue and remove 2 symbols from the preamble. And you'll see that I'm able to create messages that selectively target one receiver that the other receiver won't receive, and then we'll show it going the other way, where the receiver that missed the first messages is able to be selectively targeted. Okay, so we have our 5 fully compliant 15.4 messages that both radios receive. So now that those are done, I'm going to add 2 symbols to the preamble, and you'll see that the app emote doesn't hear anything, while the RZ USB stick is able to receive all 5. Now, I'll remove 2 symbols from the preamble, and you'll see that the RZ USB stick this time is deaf, whereas the app emote's able to receive them. So I think this is really interesting. As far as I know, this has been demonstrated on the wired case that we discussed in 802.15.4. I don't know of any other protocols that have been looked at for this type of behavior, but I think it's pretty interesting. And I want to give a shout out to David Dowd from Dartmouth, Riverloop Security, and Travis Goodspeed for doing the initial research on this to get the ball rolling here. So this brings us to the end. So we've looked at a number of different types of wireless attacks, and we've kind of made some inferences about them. Some of these are very easy to implement. Some of them are quite a bit more challenging. The cases where they get challenging are where you have essentially cryptographic state to overcome. But ultimately, one thing that I want to highlight is that many of these attacks are very difficult to mitigate against, especially the ones that involve privacy. Because RF is promiscuous, it's very hard to hide your transmissions. So it's very easy for an attacker to come in and listen and be able to figure out what's in the environment and who's talking to what, because to some extent, you can only hide that to a certain extent because of just fundamentally how the medium works. I also want to mention that this list of attacks that we've highlighted is not exhaustive at all. As you begin to go forward and work within the wireless domain, you'll find different ways to iterate on these, nuances to them, and completely new attacks in general. But we feel like this is a good list of kind of the most common things that are used and are seen, and are a good place to get started. So as we go forth, as attackers, when you're looking at wireless systems, always remember to go after low-hanging fruit first. And that's because the low-complexity attacks are by far the easiest to implement. Also, just given the state of affairs when it comes to wireless security, oftentimes you can get pretty far with them. So always start with sniffing, try your replay attacks, look for things like encryption key exchanges in the clear. After that, complexity goes up in a hurry when you have to start spoofing state and figuring out how all that works. Additionally, lean on your wired and IP network skill set wherever possible, because as we've just shown, analogs exist all over the place. Additionally, leverage open source intelligence. So open source intelligence are things like data sheets, and in the US, the FCC regulatory filings. These contain tons of information about about what physical layers are present on which devices, how they're configured. This will make your life easy. Because we like to be lazy, it's a good place to start so that we're not reinventing the wheel. In many cases, the manufacturer has already generously told us what's there and what we can start to go after. And if you're interested in learning more about open source intelligence and the process there, Marc gave an entire talk on this at Hack in the Box Amsterdam in 2016. That video is on YouTube. I encourage you to go look that up. Now, as developers and as defenders, the one point I want to leave you with is that we are right now in the golden age of RF hacking. That's because software-defined radio has been commodity for more than 5 years. There are so many SDRs out there. There's so much free knowledge from the open source community that essentially every RF PHY is in scope now. So everything is exposed and accessible to people to go and reverse engineer and begin to pick apart. So I'm going to end today with a challenge, and that's to go forth and own your airwaves. If you're an attacker, go out, start looking into wireless, and start figuring out different ways that you can subvert it and own it. If you're a defender, think about how wireless technologies are different than wired technologies and the types of exposure that your networks have. Because if you don't, it's a matter of time. The space is moving really quickly right now. The state of affairs is not very good. So if you want to learn more about this, we've given a bunch of talks on various different wireless subjects. We'll put the slide up on Twitter so that you can get the links and pursue them if you'd like. I want to thank our colleagues at Bastille for supporting our research, and also the Hack in the Box team for having us. We've had a great time, both here in Singapore and the other events we've been to in Amsterdam. So thank you for having us. And thank you all for attending, and we're happy to take your questions.
And a quick shameless plug, if you're going to 44Con, we're doing a RF reverse engineering workshop there.
Thank you. Thank you very much, Marc and Matt. We're very honored to have you here as well. And congratulations again on your talk getting voted for the stage this year. Thank you. Any questions from the floor? Probably questions off stage. All right. Well, thank you very much again.
Thank you.
Thank you.